So I'm just making the trivial observation that we have that. So if we have a function from a to b into R, and we have some x that lie between a and b, then we proved that the integral from a to b of f, this thing here, is equal to the integral from a to x plus the integral from x to b. Right? That was one of the rules, that if you take this, if you have like a dividing point in this interval, then you could integrate over the first half and then add this integral of the second half. But this thing here just tells you that this thing here you can rewrite as this minus that. So you have that the integral from x to b f of s ds is equal to the integral from a to b f of s ds minus the integral from a to x f of s ds, right? And so a and b are fixed, and when you think about this thing here as a function of x, then it's equal to, this is just a constant, and then minus this. So when you take the derivative of this is a constant, so this derivative is 0. The derivative of this, well, that is straight the fundamental theorem of calculus. And because of this sign, you get minus little f. Right? And so that's what I applied over here, that if it is of this form here, then the derivative of this function is minus little f. Okay? Okay, so this is how the angle is defined, if you will, right? The angle is defined as the length, arc length of the curve, right? And we can calculate it using this formula here, and we're getting a nice, I mean, we get, we know what this arc cosine, we know actually what the derivative is just from this arc length and the fundamental theorem of calculus. Okay. The next thing I want to talk about is, pointwise and uniform convergence of functions. So you have a sequence of functions. You have a sequence of functions fn. So suppose you have some interval I, and you have a sequence of functions fn, and you have a function, another function f also on this interval. Then we say, so this is the definition, we say that the sequence here converges to f pointwise. If for all x fixed, if you're looking at this, so x here, think about x as being, x could be anything, but it is fixed. And then you're looking at this sequence here, right? So this is a sequence of real numbers because x is fixed. Then you want this thing here to converge to f of x. Yeah?
Sorry, I had a super quick question about the last thing. So how do you know that the integral of a to b fs ds is 0?
So, no. So the thing is that what we're looking at here, so I was asking, so this here is, so if you have a function, capital F, that is given like this, the fundamental theorem of calculus gives you what the derivative is. So I'm just asking, suppose that the function that the variable was not up here, but it was down here. What is the derivative? And so in order to figure out that derivative, I'm just using that so that if I was integrating over the whole interval, a and b are fixed, right? So this is just some number, whatever it is, but it's probably not 0, right? I mean, in general, it wouldn't be 0, but it's just some constant, right? And so for each x, you get the same constant here, and then it's equal to this plus that. And so, but this is what we're interested in. So I'm just moving this one over on the other side, so I get this thing here. But remember, this here is a constant. So when you take the derivative, it's 0, right? And so, okay, so, yeah.
If you were to just substitute set b equal to a, then wouldn't you just get that a equal, like integral from a to a goes to 0, and then you can get like the same.
But if right, so. But if b is equal to a, if b is equal to a, yeah, I mean, but it's not. I mean, so then this interval is just a trivial interval, right?
Right, but doesn't it allow you to get to the same identity there? And then
right, but the thing is, so the reason why, so why did I want to do it? Yes, but it's like, but it's kind of using something implicitly. You see what I mean? I'm assuming that x is between a and b, because when we took this interval, you know, if x is not between a and b, we had to figure out what the hell do we mean by this sort of integral, right? Anyway, and so yes, it works even if you, even if you have the ordering differently, but you just have to. All I want to point out here is that if it is downstairs and not upstairs, you have to, just remember the sign. Okay. Okay, so this here, so again, so I have a sequence of functions on the interval. I have another function on the same interval, and we say that this sequence is converging pointwise to f if for all x fixed, when we're looking at this sequence, it converts to that. Right? And so let me look at two examples of that. So the first one is the first example I want to look at. This is where the functions fn of x is equal to x to the n, and x here is between 0 and 1. And so this is my fn, and my my function f, which is now of course also a function on this interval. This is equal to 0 if x is bigger or equal to 0, but strictly less than 1, and is 1 if x is equal to 1. Okay? So, of course, this function f is not continuous, the other ones are continuous. Now, I claim that this sequence, so the sequence fn is converging pointwise to f. So fn converts to f pointwise. Right? Because if you fix x, let's say fix x, and let's assume that it's between. Sorry, it's between 0. It's strictly less than 1. Right? So you're fixing x, and let's first deal with a case where that x is strictly less than 1. Well, if I'm looking at x to the n, so I take some small number Right? Small just means that it's strictly less than 1, and I multiply it by itself n time. Well, that certainly goes to 0. Right? If x here is fixed, but it's now 1, then x to the n, if x is 1, then this is still 1. Right? So you see that in this case, so this here is f to the n of x, and this here is f of x. So these things here, I mean, they're actually equal to this. So in particular, they converge, right? And this here is what f of x is, and this here is, again, fn of x. Right? So you have that this sequence of functions converge to this slightly crazy function. Right? Okay, so that's the first example. They converge pointwise. The next example I want to look at is, so the next example is where the functions are, you're just summing here. You're summing, you just take the power series for the exponential function. So you take, you're summing where k is equal to 1 to n, and that's my fn of x. And then my f of x is the infinite sum, which is the exponential function. And we have already proved that if you fix x, right? So we fix x, then this fn here of x converts to f of x, for each fixed x, for each fixed x. Right? So this sequence of functions pointwise converge to the exponential function. Now, so this is one notion of convergence for functions. And there's another notion that is also useful. They're both useful. The other one is stronger. And so, of course, if you have the stronger version, you often get something much better. Oh, I shouldn't have erased this, but anyway. So, and so the second notion is, so this is the notion of uniform convergence. Uniform means that it's uniform in x. So what we have here is we have a sequence of functions and a f defined on some interval into R. And then we say that this sequence here converts to f uniformly. If for all epsilon greater than 0, there exists a capital N, so that if little n is bigger than this capital N, then f of x minus fn of x is smaller than epsilon for all x. And again, right, the uniformness is that it holds for all x. Right? You can use the same capital N for all x. Right? And so now, now what you have is that if a sequence converges uniformly, then it converges pointwise. So you have the following lemma that follows directly from the definition. So lemma. So a uniform convergence of fn to f implies pointwise convergence. Of Fn to F. Okay, so uniform convergence imply pointwise convergence. And that's clear, that's really just the definition. If I had written out what it means for, so this here I've written out what it means to have uniform convergence. If it was pointwise convergence, right, then you have these functions again, and you have that this converges to that pointwise. It means that the sequence Fn, so once you fix x, then the sequence Fn of x, right? So once x is fixed, then this here converts to this. But saying that this sequence here converge means that for all epsilon greater than 0, there exists an n. But this n is now allowed to depend on x, so that if little n is bigger than this capital N, then Fn of x minus f of x is smaller than epsilon. Right, so you see that clearly uniform convergence implies pointwise. And again, uniform just means that this capital N can be chosen to be the same for all x. Right? Okay, so now let's look at the examples. Unfortunately, I raised like the most important one. So I will just go through it again. Let me just talk about the example again. And then we'll see why this example here does not. So we had this example from before, where the sequence of functions was x to the n, and x here was between 0 and 1. And then we had this function f. There was this function that was not continuous, but this function was given to be equal to 0 if x here strictly less than 1, and it was 1 if x is equal to 1, right? That was this function f. And we know, we already shown that the Fn converts to f pointwise, but we want to see now so I claim that Fn does not converge. So this does not converge uniformly to f. Right? We know already that it converges pointwise, and I claim that the sequence does not converge uniformly. Okay, so now why is this the case? Well, this is because you see by the intermediate value theorem, the functions Fn are continuous. At 0, they take the value 0. At 1, they take the value 1. So for each n, by the intermediate value theorem, for each, since each Fn is continuous, then there exists an xn, but it really will depend on n, so that Fn of xn will take the value 1/2, right? So the functions here, this is the functions, this is the functions, this is the function Fn. It takes at 0, it takes a value of 0. At 1, it takes a value 1. So there is somewhere where a half is achieved, and this is at this xn. Right? So you have that, and again, this xn is depending on n. And the thing is that as n get large, this point will have to move very close to 1. Okay? But if you're now looking at fn of x minus f of x, right? So we want to, if it was converging uniformly, it would mean that this difference here would be smaller than some epsilon for all x, right? But if you're just looking at this point here, this difference here is, this point here, xn, will lie strictly, xn here will lie, this is where this value here is a half. It's not 1, so it's like strictly between 0 and 1. Right? So you see that for each n, this function f at xn, this will always be 0. This is because the function f is 0 except at 1, and this point is definitely not 1. Right? So you have that. So you see that this thing here, this here is 0. So this is just the value of this, the absolute value, but that's actually a half. So this is always a half, right? So the function would converge uniformly as long as that if you, right, so uniform convergence would mean, so uniform convergence, so now let's show. So let's prove that Fn does not converge uniformly to F. Right? And so I just picked my epsilon. So I pick an epsilon less than a half, right? And then if it was converging, and suppose not, i.e., that is, suppose Fn converges to F uniformly. This means that for all epsilon, but I just use this epsilon. Yeah, I just use this one epsilon. But then I would have that there exists capital N, so that I mean I can even take it to be equal to a half. So there exists capital N, so that such that if little n is bigger than capital N, then this thing here minus f of x would have to be less than, strictly less than a half for all x. Right? If it was converging uniformly, then in particular for this one choice of epsilon, you would have this for all x. But we already know that if we looking at, now depending on what this is, but that's fine, you know, if you insert x equal to xn, then this is actually equal to a half. Right? So this here does not hold. This is the contradiction. Okay? Now, in the other example that we looked at before, in the other example, we have that in the other example, which is this example here, this sequence here is converging, and I'll return to this in a minute. So in this case, these here converge to f uniformly on each interval, on each bounded interval, so on each interval of the form minus L to L, so on each bounded interval. Okay, and we will talk about this more in just a second. Okay, and right, because this is the content of the what's called Weierstrass M-test. So this holds more generally that if you take a sequence, so you see Weierstrass M-test. So in Weierstrass n-test, you have a sequence of functions, fn, and you have that this sequence, so fn, is functions on some interval into R. And then you have that the fn are bounded by some constant mn, and then you have that the mn, so these are clearly non-negative numbers, and you have that this series here, this here is finite, right? So this is a series of non-negative numbers. So to say that it's that this series is summable is the same as saying that it's finite. And now the claim is, so then Weierstrass M-test is, so this is that if this is the case, then this sequence converts to some f uniformly. Okay, so that's Weierstrass M-test. Yep. Oh yeah, so this here means, this here just means that fn of x is less or equal to m for all x. Yeah. That's a kind of, quite common used notation. Okay, so let's try to prove that. So we are looking at suppose we define Sn of x. So this is just when you're summing from k equal to 0 to n of fk of x. Right? Suppose you're looking at this, and we want to prove, so want to show yeah, sorry about that. This is not what we want to prove, sorry. This is, sorry, I should have said, yeah. It's not these functions that converge, it's a sum of them. So what I want to prove is that, I want to prove that this thing here, as k equal to 0 to n, that these functions here converge uniformly. Okay. Right. So think about it. You want this to kind of probably apply to some power series, right? And so the individual fk is like this polynomial. It is, right? It's of some degree. Okay. So, so we define this function Sn, and I want to prove that these Sn and then converge. And if it's okay, I think it's better to call this something else than little f, to call it S, right? Because it's not these guys that converge, it's a sum of them that converge, right? So we want to show that these guys here, the Sn, converge to this S uniformly, right? That's what we want to prove. Now, let's look at the difference between Sn of x and Sm of x. And so here I'm going to think about n as being larger than m. Suppose I'm thinking about this thing here. Well, this here is when you're summing the first, I guess we're starting at k equal to 0, so then we're summing the first m plus 1, right, of those guys. Here we're summing more. We're summing those guys, but then we're also summing some more, right? And so this thing here, so let me just write it out. So k equals to 0 to n of f k of x. And the second one is when we're summing, right, n is bigger than m, so here we are actually summing fewer. And so, of course, the differences between these two are how many more of these guys are there than those guys. So this is summing absolute value, where we're summing from k equal to m plus 1 up to n of fk of x, right? So that's what it's equal to. And we didn't even have to have absolute value, but in a minute it's useful to have absolute value. Because now, of course, this sum here is less than the sum of the absolute values, k equal to m plus 1 to n, and then we take the absolute value in under the summation sign like this, right? But now we can use our condition here. So this thing here is less or equal to the sum here from k equal to m plus 1 up to n of mk, right? But those guys, right, this is just a sequence of real numbers, right? This is not a function, it's just real numbers. And they converge. So this means that you can make this thing here as small as you want, as long as m is sufficiently large, right? So given epsilon greater than 0, there exists a capital N such that if m here is bigger than capital N, then the sum here of the tail, this thing here up to anything else, right, is of this mk, that this is less than epsilon. Right? And so you see that this really say that so this implies that the Sn for each x, if you can think about this thing here as a sequence, right? And so you have that now this sequence here is a Cauchy sequence, right? For each x, this here is a Cauchy sequence. So this means that these Sn of x, they will actually convert to something, and that's something I call S of x. So that gives you a function, S of x, but it gives you more because you see it's, right, it actually shows you something about, because this inequality here, that this difference here is less than that. That holds for all x, right? So this means that as you're sending, so this means that you have, right, so now let n go to infinity. If you take this inequality here, so we have this inequality Sn of x minus Sm of x is less or equal to the sum here, k equal to m plus 1 to n of mk. So we have this inequality, and we have, in fact, you can write it as if you're summing over the entire tail. Right? And so now this side of it, this side does not depend on little n, right? This here holds as long as all here we required was that this here was bigger than that. And so as n go to infinity, you have that S of x minus Sm of x will have to be less or equal to this sum. And the key point here is for this Weierstrass m-test is that this here holds for all, this inequality holds for all x, right? You see the little n is gone, there's only this capital N, the m, right? And so now we can, so if you, as long as you choose some n sufficiently large, then if little m is bigger or equal to this n, then you can make this sum here that have no reference to x, you can make this less than epsilon, right? So this here is less than epsilon, and you have this inequality for all x, so you have this one here less than this for all x, and that's exactly uniform convergence, yeah?
Where did we get the first, like when we said that the sum of these MKs are less than epsilon?
Yeah.
Where did that come from?
Okay, so the right, so let me just I'll get to this in just a second, but let me just say what is the strategy here. So we have this sequence. Maybe I erased the statement, unfortunately. So we have this sequence of functions on an interval, and you had that these function here was bounded like this. And then you had that these are just real numbers, and you had that these real numbers here was summable. So these are non-negative real numbers, of course. Right? And so and I claim, so the claim is that the sum here of these guys, these here, I claim that these guys here converge uniformly to some function S of x. The first step is to say that there exists some function S, and they converge to that function pointwise. Right? In order to prove that, I proved that these sums here for each fixed x is a Cauchy sequence. Right? Once they're Cauchy sequence for each fixed x, then they will be convergent, and the limit I now defined to be S of x. Right? So that gives me a function. And then the thing is that I have to upgrade this convergence, which initially is pointwise, to uniform convergence. Okay? And so now you were asking, So now,
like, so we got the sum of mk's, but then where did we, how do we just set
okay,
less than?
that's right. And so now, so this here was just very general, and it just used this inequality. That's all it used, right? Now I'm using that these guys are summable. So this means that if I'm starting this summation sufficiently far out, then I can make it less than a given epsilon.
Oh, okay.
Right?
Because it's technically
because it's just like that these are non-negative number, and that they are summable just means that if I go out really, really far, then from there on out, it makes very little contribution to the total sum. Okay. Okay, so, right. So, right, and so you see, like, the first thing is, for each fixed x, I prove that this Sn of x is a Cauchy sequence. That then allow me to define a function, S of x, and I get that the sequence Sn of x is converging, the sequence function is converging pointwise. And then again, once I have that, then I need to upgrade it to be uniform convergence, and that's what we did here. Okay. Okay, so now let's try to apply this. Yeah.
So what if the MKs are a kind of converging sequence that, but like the small side, the zero side, is on a low index. So then, like, as I go further out, it's getting bigger.
Can we look at an example and see if it becomes clear? So let's look at a sort of, let's look at an example. Let's look at it so let's look at an example. So in fact, let's look at the function, the example we just looked at, but we said that it followed from Weierstrass M-test. So what was the example I just looked at? So I take a function fn of x. This is now x to the n divided by n factorial. Okay, now I define Sn of x. So this is now the sum from k equal to 0 to n of these fn of x, fk of x, sorry. So this means that this thing here is the sum from k equal to 0 to n of xk over k factorial. Okay, and I want to show that these, that these Sn of x converge to the exponential function uniformly on an interval of this form. So L is some fixed number, and I'm looking between minus L to L, right? And I claim that they converge. Okay. Now let's try to apply Weierstrass M-test, right? And so what are the Mn? The Mn, in this case, the natural one is n to the power n times n factorial. Okay? If I'm looking at those numbers, these are non-negative numbers, right? And we already know that this sequence of non-negative numbers is summable. That these non-negative numbers like this, that they are summable. Right? And so then, and suppose now I take these n of x. So this is this function x to the power n over n factorial. X here, remember, is in this bounded interval. Well, let's look at fn of x. So this is x n over n factorial. But this thing here, so this is just x to the power n factorial. This is lying in here, so it's its absolute value is bounded by L. So this is L n over n factorial. Right, so I have that this sequence is less than these mn. Right, and so now Weierstrass, but we restrict to this interval here. And so now Weierstrass m-test tells you that the sum here, when you're summing from k to 0 to n xk over k factorial, that these actually converge to the limit uniformly on, but remember we are restricting. So, and the limit here, we already have defined the limit to be the exponential function. Okay, is that clear or not? Does that answer it or not really?
I'm not sure.
Okay.
So I guess my question was,
yep.
Is it that mn must be a convergent series?
Yeah. So mn, that's right. So mn are, in this example or in the general example, so why is the mn so much easier to determine? Because they are just numbers. They are just non-negative numbers, and you're just asking if the series of non-negative numbers is not function, it's non-negative numbers, if that's convergent or not, right? And so since they're non-negative, it just means that the sum is finite, right? And so that's much easier to determine. Okay. Right, so now we can do this sort of same argument more generally. So this leads us to the following. That suppose you take a power series. So suppose you take a power series. So you're summing here n equal to 0 to infinity, an xn. This is a power series, right? So power series, remember that a power series is where you're taking a sequence of numbers, real numbers, and you think about these as coefficients in this polynomial, and then you're summing over them, right? But it's like, it's the an is the coefficient to x to the power n. Okay, so this is a power series, and a power series again means, so like you think about it as a series, because like for each x, it's like a regular series, right? But then it's like the value of that you get depends on x, right? And so for this, we define the radius of convergence. And let me remind you how this radius of convergence was defined. You take the an and you take the absolute value of it, and then you take the n root of that. And then you're looking at lim sup as n goes to infinity. Right. That gives you some number. That number potentially could be infinity. It's always non-negative, and it will always give you a number. It could be 0, it could be infinity, and it could be anything in between. And then the radius of convergence of the power series is, so this is what I write by R, and this is 1 over m. And where there's this convention, in this case, usually you don't divide by 0 or infinity, but in this case, if m here is 0, this means that the radius of convergence is infinite. If m is infinite, then it means that the radius convergence is 0. And now the sort of slightly surprising fact, but we proved this, but I'm just reminding you about it, that the thing is that the power series is convergent. So here you have 0. It's convergent inside. If this here is R, it's convergent inside here, and it's divergent outside. But it's not completely clear what happened on the boundary, right? So you have to check the boundary, separately, and that depends on the power. There's no general formula for that. Okay. So now the theorem here is that. So the theorem is like this, and this is just generalizing this example that we just did. And the theorem is the following: that if you take a power series, so if you have a power series and R is the radius of convergence, and L here is strictly less. It has to be strictly less than the radius of convergence. Then these functions here, k equal to 0 to xk, that these functions here converge to the limit here. Uniformly on this interval here from minus L to L. But remember that L had to be strictly less than the radius of convergence. Okay? And so this is like extremely useful. Like if you have, and it will be clear next time why it's useful, because if you have uniform convergence, then it becomes very easy to, if you have uniform convergence, then you can argue about if you want to take the derivative of integrating this thing over here. If you have uniform convergence, then it will say that then a lot of operations, we'll be more precise about that next time, but a lot of operations like integration and differentiation, you can do that over here and then go to the limit. So instead of, if you were to integrate this thing here, right? So just say that, but this seems maybe very, very hard. But the thing is, if you can integrate here, then you can just use the usual sum, the usual formula for the sum, it's just a sum of the integral, and likewise for differentiation. Okay. And so, maybe I will just, maybe I'll just stop here. I wrote out the proof in the notes, and I already posted the notes, the lecture notes. Are there any questions? Okay, great.